All right, let's get started. Good morning. All right, so today we're going to look at section 13.4. The good news here is that you basically know everything we're going to be talking about already. We'll be talking about velocity, position, and acceleration. And all of those things you have some familiarity with, but a little bit of difference here and there. We'll take a look at that. Okay, so this section deals with motion in space. And of course, we're talking about velocity, position, and acceleration. Pretty much everything you know from Calc 1 dealing with scalar functions still applies. So for instance, suppose that we have some object and we're going to track its position in a three-dimensional space. Okay, so as time goes on, this thing is doing whatever it's doing. And each point here is just some x, y, and z. Okay? And stuff you know, like I said, from earlier calculus or physics still applies. For instance, if we want to find the average velocity over the interval t is between t1 and t2, whatever t1 and t2 are. Right? So how would you find this? Think back to what you already know about the average velocity. If I tell you it took me an hour to travel 65 miles, what is my average speed? 65 miles per hour. And how did you find that? Exactly. You take the difference in the positions and then divide it by the difference in time, right? So this is, we'll call this thing V with subscript, what does the book use? AVE, okay, good enough, average. The only thing different here is now we're talking about vectors. So we have a vector function, we're talking about the vector velocity. This will be the position at the later time, t2, minus the position at the earlier time, divided by the difference in time. The difference in where you are divided by the difference in time. That gives you your average velocity. Just think back to my 65 miles per hour analogy I just gave you. So that's the average velocity. What about the instantaneous velocity? Derivative, right? The rate of change. So the instantaneous velocity, usually just v, is of course just the first derivative of the position vector. What's the relationship between the average velocity and the instantaneous velocity? Very good. So is there a way I could, what's the relationship between them? How can we turn the average velocity, how do we approximate the instantaneous using average? Yeah, exactly. When the time interval is very, very short, right? So the relationship between these two is that as the time interval shrinks, meaning T2 is getting closer and closer to T1, the average velocity approaches the instantaneous velocity. Okay, so essentially, if you remember back in Calc 1, this was the average velocity was the secant line slope between 2 points. The instantaneous velocity is the tangent line. And to get a tangent line from the secant line, you bring the second point closer and closer to the first point. And eventually you get your tangent line. So all of this stuff you already have seen. And the only thing that really changes here is that we're dealing with vectors now. But we're dealing with a vector of scalar functions in each component. So R of t generally is the position. And the instantaneous velocity, or simply just the velocity, is the first derivative. What do you call the magnitude of the velocity vector? Speed, right. And the acceleration vector is the derivative of the velocity vector, or the second derivative of the position vector. So velocity is the rate of change of position, acceleration is the rate of change of velocity. What's the rate of change of acceleration? Jerk, yes. And where do you use jerk? Physics, okay. Give me very good. Any more real-life example that you can think of? So jerk measures the change in acceleration. And if the change is too big over a very short amount of time, it can damage things such as the human body. So for example, if you're designing a roller coaster, you want to track the jerk, the quantity, the jerk, because it tells you how fast the acceleration is changing. You want to keep it under a certain value so that people riding that roller coaster don't get hurt. We can handle acceleration up to, I think a trained pilot can take maybe 12 G or something. But the change in the acceleration, that's a different story, and that's something that a human body doesn't handle very well. Okay, anyway, we generally don't deal with jerk that much, but in physics, you'll see that once in a while. Okay, now let's look at this thing here. Let's go back to what we talked about last time. I want to talk about the arc length formula. So yes, last time we looked at this, we said the arc length is the integration of the magnitude of the derivative of the position, dt. Let's reinterpret that in the context of velocity and distance and acceleration and all that. So looking at this formula here, this right here, this is our speed, right? That's the magnitude of the velocity vector, so that's our speed. And this here, this is a time interval. Which is very short. because we've taken the limit to allow the time interval to shrink. So, and we also know distance times time is velocity, speed times time is distance. So then what this formula is doing is an infinite sum of a bunch of little distances, one little chunk at a time. So you think, so that's how we get the arc length, right? How far you have traveled over a certain time interval. For example, suppose I have the speed of some object at certain points. Okay, so this thing started with 15 feet per second speed. 10 seconds later, it went up to 20. 10 seconds later, went down to 10 and held it constant. And using just the data here, we can approximate the distance that we have traveled, right? So during the first 10 seconds, we can take the beginning speed as the speed, the average speed, 15 feet per second times the 10 second, times 10 second difference. This is on the interval 0 to 10. And then for the next 10 seconds, we do the same thing. Interval from 10 to 20. And then 20 to 30, we do the same thing again. We get 10 times 10. Right, you see what I'm doing here? This speed times the time gives me distance. Right, so this gives us something 150, this is 200, and 450. And what we're doing here, this is just an approximation of an integral. If we want the exact distance here, we need to shrink the time. And that's where this formula is telling us. You take the speed, which we got, and now we need to shrink the time. So this is not going to be it's not going to be exact, but probably a pretty good approximation. Okay, does that make sense, the reinterpretation of the arc length formula in the context of speed? Yeah? Okay. All right, we also know that if I take the integral of the acceleration vector, I get my velocity. But now we're going to be careful. We've seen this before. When you integrate a vector value function, you will get a vector constant of integration. All right, so this is a vector constant of integration. Basically, each component of that A vector is going to gain one constant. So you're going to have a constant in I, a constant in J, constant in K. You bring them out, and that's a new constant vector. Has I, J, and K components. So just like stuff like you already know, the only different thing here is we're dealing with vectors now. And of course, the integration of velocity gives us the position. Again, plus some constant vector of integration. All right, let's do one example with a few functions that we can differentiate and integrate and all that. This curve is 2 cosine t, 2 sine t, and 5 cosine squared. Can you visualize this shape? Can you at least see the projections into each dimension? For example, let's cover up z here. Look at x and y. We see that if I square x and I square y, I'm going to get 4, right? This is telling me that in the xy plane, if I just look at the xy plane, looking down at this curve here, I see a bunch of circles. Make sense? We've done this before. And looking at the x and z, for example, this is saying that z is equal to some constant times x squared. So in the x and z plane, we see parabolas. Yep. Same thing in the y and z plane. So this shape is think of a circle, and then you stretch it out a little bit and then bend it down like that. So from the side, you see a bunch of parabolas, but looking down, you see a bunch of circles. It's kind of a warped circle. Okay? So that's the shape we're dealing with. And the good thing is that even if you can't visualize this, if I give you this and say, find the velocity, you can still do it. All that takes is differentiation. Derivative of cosine is negative sine, right? So minus 2 sine t. Derivative of sine is positive cosine. How do we differentiate cosine squared? Chain rule. Yeah. So think of this as 5 times cosine t squared. When we differentiate this, we bring the 2 down, right? Times 5. Reduce the power by 1. And then the chain rule kicks in. We need a derivative of cosine, and that's negative sine. See that? Yes? Good. This is negative 10 times cosine times sine. To differentiate again, it's useful if we can rewrite this a little bit. You can use the trig identity. Sine of 2t is equal to 2 cosine t sine t, to rewrite that. And that's not strictly necessary, because if you want to differentiate again, you could use the product rule here in that form, or you can use the chain rule again in this form. It's just an option. It's not strictly necessary. All right, acceleration. This is easy. Derivative of velocity. Do it again. And here we're using the chain rule again, we get minus 5 times the derivative of sine of 2t, right? So first we get cosine of 2t, and then the chain rule requires another 2. So at the end of that, we get this expression, minus 10 cosine of 2t. Right? Okay. Questions? Pretty easy stuff, yeah? You already know it. So, okay. Let's look at this next example then. This time the position vector is radical 2t, e to the t, e to the minus t. Does that function look familiar? Yeah, that guy caused a bit of a trouble, yeah? Was my solution helpful? Okay, good. All right, so let's find the tangent vector and normal vector. No, we're not going to do that. Let's do something else. At what t is the speed a minimum? By the way, on the exam, we're not going to ask you to find a normal vector, for example, with that function. You saw how long it took. That's just too much. We'll give you something a little bit more, a lot more manageable than that one. Okay? So don't worry about it. It's a fine exercise for homework since you have so much time, so many attempts, and you have help. But on the exam, that's too much. So don't worry about having to see that on the exam. Okay, so we need to find when the speed is a minimum. So we got to get to the speed, right? To get to the speed, we need a velocity. And that's very easy to find. Now let's find the speed. Speed is the magnitude of the velocity. This is a t, sorry. So velocity, remember, has a direction. A speed doesn't. Speed just tells you a magnitude, the length of that vector. It doesn't tell you which way it's pointing. Magnitude is the square root of the sum of squares. So 2 plus e to the t squared plus negative e to the negative t squared. So that's a plus because we squared this thing already. And you saw on the homework problem that we could rewrite the stuff under the radical as a sum of squares. Radical of e to the t plus e to the minus t, the whole thing squared. So that makes the speed a very, very compact expression. Without the root, it's just much nicer than this thing. By the way, which sign do I take when I take the square root? Why not a negative? Right, speed is positive. So we got to make sure that this stuff, e to the t plus e to the minus t, is positive. If this is positive, then I take the positive root to make it always positive. The end result is that speed has to be positive. And you know from Calc 1, exponential functions are always positive. So this ends up being our speed. Always positive. Okay, so let's. Okay, so let's go backwards here with this thing. Let's look at this one. Let's work backwards. All right, so when I square a plus b squared is a squared plus 2ab plus b squared. Right? So you see, this is e to the 2t. E to the t times e to the minus t is e to the 0, and that's a 1. So there's your 2 here. And then this guy here is e to the minus 2t. Does that make sense? Is that okay, everybody? Yeah? All right. Okay, so let's call this thing speed s of t here. Now think back to Calc 1. How do you find the minimum or the maximum of something? It's a scalar function, so you know how to do it. You take the derivative and then make it equal to 0, and then I'm not hearing a lot of... And then you find the critical numbers, and then you... Let's do it. All right. So s of t, s prime of t, is e to the t minus e to the minus t. And that's the rate of change of the speed, right? It's also the acceleration. You make this equal to 0. So this equation is saying if I move this over to the other side, e to the t is equal to e to the minus t. If I multiply both sides by e to the t, I get e to the 2t is equal to 1, right? So this seems pretty obvious. The only way this can be true is if 2t is equal to 0. So t is equal to 0. And this means that the speed could be a maximum or a minimum at t is equal to 0. Now remember, finding that number alone doesn't guarantee that you get what you want. It tells you that there is a potential to find the maximum or the minimum there. And how do you know which one is which? How do you check if we have a maximum or minimum? Yeah. Right, so we can use the first derivative test or the second derivative test. Either one is fine. Yep, good. Let me just copy what we got there. All right, let's do the second derivative test here. Because this function is so easy to differentiate, we might as well do that. And you plug in the critical number, and we get 0, we get 2. What does 2 mean? It's positive. What does that mean? Concave up, so therefore we have a minimum. Very good. So this is positive. So S of t is a minimum at t is equal to 0. And that means the minimum speed is s at 0, which is equal to 2, right? 2. 2 feet per second, miles per hour, whatever the units are. Questions? You know that stuff already. You might have forgotten, but you know the stuff already. So it's not new. Okay, let's look at integration for a little bit. The only thing to pay attention to is that constant of integration. Let's suppose that the acceleration vector is 7I plus 8j. Suppose that I know that v, which I don't have yet, at 0 is k, and r at 0, which I don't know yet, is I. Let's find the position vector function. All right, so these things are necessary to find the constant of integration, the two constants of integration, vectors. And these are often called the initial condition. You'll encounter that term in your future math courses when you do differential equations and all that stuff. These are called initial conditions. The reason is because just knowing the velocity or the acceleration is not enough to reproduce the whole history of the object. To find the velocity, we integrate acceleration. It's a constant vector, so we can do that. We can do that, at plus j, plus some constant of integration, right, c. Let's call that c1, because we're going to get a different c later. So that's very important to remember that this constant of integration you get is a vector, has three components in the three-dimensional world that we're dealing with. To find C1, we use the fact that this v of t, which is equal to that, at t equal to 0 is equal to k. This is the condition that's provided to me. So I take my function, my v that I already got, I put in a 0 for t, so I get 0i, I get 0j plus c1. I don't know what it is yet, but I know it's a constant. It doesn't depend on time. And now I also know from the provided condition that this is equal to k. And here it seems very obvious that c1 must be equal to k, right? So therefore, v as a function of t, we know completely about this function now because we know the unknown constant is 7ti plus 8tj plus c1, but we found that to be k. All right, so we got my velocity. To get the position, we integrate one more time, and we do pretty much the same thing. (7t) integrating that, we get 7 over 2 t squared I plus 4t squared j. What do I get when I integrate k? tk, right? Because this is 1k, integrating 1 gives me a t, so I get tk. and one more constant of integration. Once again, remember that's a vector constant in general. Well, always a vector constant, right? Okay, using the other condition here, we know that r at t0, from my function I get 0, 0, 0. Plus C2. And I'm also told that's equal to I. So this means C2 is equal to I and therefore the complete uniquely determined vector function for R is 7 over 2 t squared plus I, there's an I over here, 7 over 2 t squared plus 1I 4t squared j plus tk. Okay? Okay, so this is very easy to do. It's a very simple process, very easy steps. If you think about this, every time someone throws you a baseball, football, or whatever, this is what our brains are doing at that instantaneously. So what we do is that we just know that if the only acceleration that's dominant is the gravity. And just by looking at we need to see the ball at least once. That's equivalent to knowing one of these vectors. And when we look at the ball, our brain just automatically picks up the velocity based on the position of that one point in time and the velocity that we know. You know where the ball, more or less, where the ball is going to be. And you look at athletes, they just move automatically to where they think the ball will be. Our brains are evolved to do stuff like that. And we do that very well as long as the acceleration vector is constant. Now, when there's wind and wind is rapidly changing directions, even professional baseball players sometimes miss the ball, right? If the velocity acceleration is not constant, our brain can't pick up that very, very well. And we need to see the ball at least once. Imagine if someone's throwing a ball and you're blindfolded. And even if I tell you I'm throwing the ball directly at you at 10 feet per second, you're probably not going to be able to catch it, right? So you need to see that at least once. Without seeing the ball, you don't know these vectors. Without seeing the ball, you don't know the constant vectors. That's why you can't reliably catch the ball. And it's pretty amazing if you think about it that our brain, not just our brains, but most animals' brains, especially predators, they can pick up the motion of their prey very, very reliably. Okay, anyway, let's talk about this thing that we see a lot. You probably see this in physics. Projectile motion. And you probably have seen the equation in physics. And here, let's see how those equations come out. Let's assume that the only force here is gravity. And gravity, we'll call that G, goes in the negative y direction. So this is what happens when I'm throwing a baseball at you, for example. To you, not at you. And we know what's going to happen. The thing is going to have a parabolic path, right? And you probably know from physics that the x and y components are independent. They don't affect each other. And we're going to see the equations telling us exactly the same thing. looking at this right here, if the only force is gravity, that means the only acceleration is gravity. Force and acceleration are the same thing because Newton told us that. And our acceleration vector here is gravity, g times negative g times j, because j goes in the I direction, so going down would be negative j. So magnitude is g, 9.8 meters per second squared in the SI units, and in the negative direction, so negative j. When I integrate that, it's very simple. We get negative gt j plus some constant, vector constant of integration, c1. To find c1, we need to know v at one value of t. Right? That's like I told you earlier, that's equivalent to you seeing the ball at least once for your brain to pick up that constant vector. So let's assume that we throw the ball with a constant initial velocity at t equal to 0. And let's call that vector v sub 0. And let's say that I'm throwing this ball at an angle of alpha from the horizontal, 45 degrees, 60 degrees, whatever. So this tells me that v at 0 is v sub 0. What we need to do here is to break this into the I and j components. If I form a triangle at the origin here, the hypotenuse is that initial velocity, the magnitude is v sub 0. And it's made out of sum of two vectors. One vector going in the I direction. And this one is v sub 0 cosine of alpha. And this is v sub 0 sine of alpha going up. And you get this by just using your trig identities. Cosine is opposite over, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and so on. So this tells me that v at initial time is equal to v sub 0 cosine alpha I component plus v sub 0 sine alpha j component. Sorry, those things are running together. Okay, so that's what we need to find out our first constant of integration. Now I plug in t equal to 0 into here. At t equal to 0, the only thing that survives in my function here is c1. But we also know it is equal to this. So this is automatically my constant vector. And you've seen in the last example too, if you know the initial time and this thing disappears, then this turns into the initial vector. So at the end of that, we get this guy plus minus GTJ. So we get this thing plus v sub 0 sine of alpha minus gt j. And this equation makes perfect sense. We only see gravity in the I component because we know gravity doesn't affect the horizontal component, right? If I slide an object across this bench right here, gravity has nothing to do with it other than keeping the object on that bench. Provided that the friction is not too much, there's really no difference between me doing that here or on Mars, for example. Gravity doesn't directly affect it, but the object you toss straight up comes back down, and comes back down because we have gravity. Without this term right here, this thing is just going to go on forever, right? So it makes sense that we only see gravity in the j component, up and down. Let's integrate one more time to get position. Let's assume that at the initial time, I'm at the origin, so 0i plus 0j. And when I integrate the velocity vector to get my position vector, this right here, even though it's got symbols all over the place, this thing is a constant. There's no t right now. When I integrate that, it's a constant. So I gain a t out of that. Okay, so it's that thing times t I plus, now we got this thing here, it's a constant and something that depends on time. So here we get v sub 0 sine alpha t minus 1/2 gt squared, and all of that in the j component. And of course, some, as of now, unknown initial constant vector. And then we use the fact that we assume that initially we are at the origin to find the vector C2. By the way, this is the zero vector. If you see a zero with an arrow over that, that's a vector. It's a zero vector. A zero vector is zeroing every single component. If I don't write the arrow here, then that's a scalar. I can't have a vector equal to a scalar. That doesn't make sense. There's no such thing as a vector equaling to a scalar. So if you plug this condition into the last equation we got over my left shoulder, you see that C2 is equal to 0 very quickly. So that means my position during the parabolic, the projectile motion here is this equation. That's an I, sorry. That's a J here. Yep. Okay, so you probably have seen these equations probably given to you in the component forms, in the horizontal and vertical components in physics. But that's where these equations come from. We integrate everything from the fact that we know the only thing acting on the object is gravity. Now, once you introduce things like air resistance into the equation, it gets very complicated because air resistance usually goes against the motion. So it's changing with time as the object is flying. And that's a very, very complicated problem to solve, which you don't have to worry about yet. Okay? All right. That's it. Have a good weekend. See you Monday.
There we go.
Gotta be happy.